Hello, fellow problem solvers. So they're going to be doing an introduction to functional equations. First, what is a function? So a function is defined with two sets, and it's a mapping from set A to set B, such that every element from A maps to or has an arrow to an element in set B. So if you were to think of it as there's a set A, there's a set B, it can be finite, infinite, doesn't matter. And you take all the elements from set A, there are some elements in set B, and you point arrows where they go to set B. You see, the only thing is there can only be one arrow from an element in A to one element in B, right? This arrow can't go both to this element and this element, but it can go, but there's multiple arrows can go to the same element. And there might be some elements in B which no arrow maps to. And that's a possibility. Now, a function which has certain properties, for example, a property that no two map to the same element, has a name, and a function with a property that everything in B has something mapped to it also has a name. And they have a name not because a name is important, but in mathematics at least, but because these things come up and can be useful sometimes. So that is what a function is. And examples of functions is, say, a function from the, say, natural numbers to 0 and 1. It can be f of 1 and f of 2 is 0, and f of n is 1 for every other n. Right? It doesn't have to be a polynomial. It can be any old mapping, right? It can be, we usually map numbers to numbers, or sets of numbers to sets of numbers, and just because there's a bijection between any collection of things and numbers. So we always map these numbers to numbers, and it doesn't have to be sensical. It can also be f of n, for example, is congruent to n modulo 3 if a function is from the integers, the positive integer, the natural numbers, to 0, 1, 2, 0, 1, and 2. Or you can have just a function f of n to n, and it's, for example, everything just goes to 1, right? You don't know, like everything, yeah, that's just an example of a function. Now, a good way to sort of figure out how do we solve functional equations is by actually trying to solve functional equations. And these are two problems. And you're trying to see really, a functional equation tells you this is something that holds true for, so this is, for example, is a function from the integers to the integers, and it says this thing holds true for every single pair of integers. Can you determine what this mapping needs to be? Right, that is what the problem is asking you. I'm saying 1 is mapped to 1, everything else is mapped to something. You will find out what that is, but it must satisfy if I take x plus y, that it will be f of x plus f of y. That's the thing. And with that, let's try, 5 minutes. If you have never seen functional equations before, just pause for 5 minutes and ask yourself, how would you find all mappings, all functions from the integers to the integers such that this is true, right? And now we're going to do just that. So we have this function, right? And we know that there's a mapping from 1 to 1. 1 maps to 1. And now we need to figure out everything else. Does it need to map to something specific? Like, can it be anything? Can 2, for example, map to 1 again? Right? If f of 2 is 1, that's what it means for 2 to map to 1. F of 2 is 1. Will this functional equation still hold true for every x and y, every pair of numbers x and y, which are in the integers? And the way we check this, really, is by, so there's checking this on one hand, and there's, okay, let's actually check this out. If f of 2 was 2, f of 2 was 1, not 2, would this still be true for every single pair? And we can check, okay, let's put x is equal to, say, 2, and then we would have that f of 2 plus y would need to be equal to 1 plus f of y for every single y, right? Does this hold? Like, we don't know where the other y's land, but if we say plug y is equal to 1, we would have then, oh, f of 3 would also need to be equal to 2. There's no contradiction yet. Let's try something else. Let's see if we set This is setting x to 2. What if we set x plus y is equal to 2? Or in other words, we're setting y is equal to 2 minus x. It's the same thing. So then we would have that f of 2, which is 1, would be equal to f of x plus f of 2 minus x for every integer x. Now, is this always true? Well, if we put, say, x equals to, say, 1, we would have this is going to equal to f of 1 plus f of 1, which is equal to what? We know it's 1 plus 1, which is 2. Oh no, 1 and 2 are not equal, so this is a contradiction. So f of 2 cannot be 1. And the way we're sort of figuring out what f needs to be is by plugging in, not just by guessing, oh, is f of 2 1, is f of 2 0? Like sometimes you can do that, but generally what you want to try and do is to, instead of all the values of x and y must satisfy this, let's plug in specific ones and see if that implies anything. And here, for example, when we plug in y is equal to 1, what do we get? We get that f of x plus 1 for every integer x is equal to f of x plus f of 1. F of 1 is 1, so we have f of x plus 1 is equal to f of x plus 1. And now we have figured out that there is also a relationship between two neighboring natural number integers. We have a relationship between their f's, ones which are neighboring, and a relationship that relates something to the other integers. And now here, this is what we're going to be doing in these functional equations. Now we plug in, say, x equals 1, and we get f of 2 is equal to f of 1 plus 1, which is equal to 2, because this is 1. We have f of 1 is 1. That's what matters. And then we have f of 2 is equal to 2. And then furthermore, we can now plug in, say, if we want to get f of 3, what is the thing that 3 maps to? We just plug in we plug in x equals 2, and we'll get f of 3 is equal to f of 2 plus 1, which is 2 plus 1, which is 3. And then via induction, we can show that f of n is equal to n for every positive integer n, right? If we're just like plugging in like this positively. Now, we don't know anything about the negative integers just yet, the way we've so far done the proof. The way we would do this for the positive integers is, say, assume f of n is equal to n, like our base case is n is 1, 2, 3. And then assume f of n is n, and then we'll prove that we have f of n plus 1 is equal to f of n plus 1 by this relationship, plugging in x equals n, y is equal to 1, and we have this is equal to n plus 1, which is what we needed to prove. So we have it for all the positive integers. Now, I invite you here to pause. I'm going to take this in for the next 5-10 minutes and try to do the negative integers. Okay? And here's that step. So, again, we're going to be using this. Now, instead of me focusing on here what I want to get, I'll put x, the thing I want to get. For example, I want to get f of 0. I know f of 1. Plug in x equals 0, and I get f of 1 is equal to f of 0 plus 1. This is already equal to 1, which means f of 0 is 0. And then I can do an induction in reverse, like I can do the induction of the negative numbers as well. That's one way of going about it. Another way of going about the same thing is, once I have this, if I plug in x is equal to some n and y is equal to negative n, what will I have? I will have f of n minus n is going to equal f of n plus f of negative n. And now this thing right here is f of 0, which is 0. And I have 0 is equal to f of n plus f of negative n. And now what do I have? If I plug in a positive integer n, then I'll have that this number here is equal to n. Then I'll have f of negative n is going to be equal to negative n when I move this here. And by that, I've covered all the negative integers as well. So usually, and now we have f of x equals x for all x which are in the integers. So we have now shown, let me just say a couple of things. We have now shown that this function that satisfies this for all pairs of x and y, when we plug in a subset of all the pairs, right? We've really just been plugging in pairs of 1 and n, every pair of what x equals. Actually, we've done y equals 1 and x equals n, and we've plugged those pairs in, and we've plugged pairs n and negative n for every single integer n, right? Those are the pairs that we have tested out, so to speak, on our function. Those are the pairs that we've tried. However, and what we've come to the conclusion is that we've concluded from plugging in those pairs that f of x needs to be equal to x for every integer x. But what we haven't shown is that this is what just plugging in those couple of pairs has led us to, this needing to be true. But the question is, does this equation then satisfy for any other pair of x and y that we haven't plugged in? Is this true? If this is what f is this true for any other pair? And here the answer is yes, because now f of x plus y is going to be equal to fx plus y, and this is true for every pair of x and y. But we always need to check that what we've figured out that f needs to be by plugging in a subset of all the possible inputs to these to the functional equation. We need to check that once we narrow down what f is, that then we need to go back and say, okay, does this thing we've narrowed it down to actually satisfy everything else we haven't plugged in? And that's why you need to check at the end of it. Now, I invite you with this in mind to try to work on this problem for the next 10 to 20 minutes and see if you can get a hang of what it is. Now here we are in the rational numbers to irrational numbers, so it's going to be a bit more tricky, but I suggest you try out, see if you can maybe work with the natural numbers first, like the positive integers, and then go into the negative ones, okay? And here's the next step. So what do we have? We have f of 1 is 2, and f of x times y is f of x times f of y minus, oh, it's a lot of stuff. Let's write it down here. So we have f of x plus y, and plus f of xy is f of x, f of y plus 1. I like to have my pluses on one side, like pluses on both sides. F of x, f of y, and then the answer plus 1. So, and we know f of 1 is equal to 2. What do we do here? Well, we know the value of f of 1, and this is sometimes what you'll do is you'll say, okay, I know the value of f of 1. I know I have this value. Like you're trying to get usually a couple of concrete values, and then you're trying to get from there to more values. Because like the more values of f you know, it sort of seems like the more everything is constrained. And the more everything is constrained, the more you can get to the actual only solution or solutions to a function. So here we have f of 1 is 2. So let's plug in 1. And I usually like to go by plugging in one after another. I don't like to plug in 1 immediately, for example. X equals 1 and y equals 1 immediately. I like to plug in one member of the pair and then see what happens. Because, I mean, here in a symmetric function, there is no need to look at something else, but I like to go one pair at a time because there are more things that hold when I just have y equals 1. Like I'm having more degrees of freedom and I can see, okay, what kind of x do I want to pick? But I first put in y and then I see, okay, now with this y, which x will I pick? Like, I might be wrong in just plugging in x equals 1 equals y immediately. I might miss something, but if I plug them in one after another, I could maybe see everything I need to see. So That's just a sort of tip here. And what do we have? For y equals 1, we have f of x plus 1 plus f of x is equal to f of x times f of 1 plus 1. Now, f of 1 is equal to 2. So we will have f of x plus 1 is equal to f of x plus 1. And now, just like in the previous problem, we now have this relationship, and we can get that f of n is equal to what? For every positive integer n. Pause for 2 minutes if you haven't. And the answer is this is equal to n plus 1. Why? F of 1 is equal to 1 plus 1, which is 2. And then when we plug in 1, we will have f of 2 is f of 1 plus 1, which is going to be 2 plus 1, which is 3. And then inductively, if we assume we have f of n is n plus 1, then f of n plus 1 will be f of n plus 1, which will be f of n plus 1 plus 1, which is n plus 2. And we can do the induction in reverse as well and get the negative integers as well. Now, if you haven't gotten that f of n is equal to n plus 1, mind you, for which n? For all n which are positive integers, but you can also do this in the negatives. Assuming that, like if you're in the negatives, what will you do? I invite you to pause for 2 minutes, ask yourself, what will you do if you have negatives? You'll say that it's true for some minus n, where n is a positive integer, right? And then for minus n minus 1, what do we have? Well, when we plug in x is equal to minus n minus 1, then x plus 1 is minus n. And then minus n is going to be equal to 1 minus n. And then when you put this on the other side, you'll get 1 minus, you'll get the ones cancel out, but you'll get f of minus n minus 1 is going to equal what's it called? It's going to be equal to 1 minus the n minus 1. Yeah, I think that's true, yeah. Which is equal to minus n. And you'll prove by induction that f of n is n for all n, which are in the integers. Now with this, I invite you to pause for 5 minutes and ask yourself, what is it that we have? And here's the answer. What we have is that f of x is equal to x plus 1, but only for which x? Only for x which are integers. We have not even touched the rational numbers just yet. So it's important to keep in mind that we are not even close to done. We've shown that this function needs to satisfy for the integers f of n is n plus 1. We haven't done anything about the rationals yet. And now you might say, oh, but should we maybe check that this thing is good for the integers? And usually you want to hold off on that until you actually see that, and you'll check everything out at the end. Because if f of x is x plus 1, f of x equals x plus 1 is a solution for every x that's an input in a function, we can just check it immediately by plugging that in here, and we can look at all the numbers, not just the integers. Like you can get 2 birds with 1 stone, the positive integers and the rational numbers which are not integers. I said the positive, I meant all the integers. We can get both of them in one go. So we lay that off till the end, and now we need to see how do we get to the rationals. And rationals are numbers of the form what? And they're numbers of the form p over q, where p and q are relatively prime. Now, how are we ever going to connect the rationals to our integers? It does not seem simple. Now, let's see if when we plug in, say, where would you plug in a rational? And take into the fact that you know f of n is equal to n plus 1, you have values for the integers. So what would you do? Pause for 3 minutes, ask yourself, what would you do? What would you plug in? And here's what I would do. I would actually just look at x times y if I plug in, say, p over q here, then I can have, if I say like y is p over q, I can say x is equal to q, and then I make this a integer. And I'll have y as an integer, I'll have a rational and irrational. I'll get two rational numbers, which I'm not sure what they are, but I'll also have an integer. So let's plug that in. And what do we see? We see x plus y is going to be q plus, so we're going to have f of q plus p over q plus f of q, actually f of p, is equal to f of q times f of p over q plus 1. We know what these values are. This is p plus 1, q plus 1. I'm not writing that just now. And the question is, can we relate these two in any way? And initially, to me at least, it seems like we're having a little bit of a difficulty doing that, right? How am I relating this number to this one? Like I'm having a relationship now between these two numbers. P and Q don't need to be relatively prime. Maybe that could give me something, like the way we plug them in. So is this good, or should we plug something else in? Does this give us something nice to work with? That is usually the question we ask ourselves here, because really what this gives us is f of q plus p over q is going to be equal to this, actually this plus p is equal to f of q is equal to q plus 1 times f of p over q. The ones cancel out. And to me, it doesn't seem like this is something that's incredibly nice to work with. This is nothing that's like an additive thing. This type of function we had here is called a Cauchy function and has nice properties. Sometimes the problem is if you can get a problem down to a Cauchy, or something that looks like Cauchy, you can immediately solve it. And this is like where memory is useful in mathematics in general, like when you remember interesting problems, why I think it's good for you to have like an emotional reaction to like, oh my God, that was a cool problem, because then you'll be more likely to remember like, oh, I remember I had this, you're working on a problem, you get to some place and you're like, oh, I remember I had something like that before and I solved it like this, and then you remember that. So this right now seems like a dead end. What do? We can cry, we can be sad, but maybe we can also just see what else we can do. Like we plugged in two values at the same time. Why do we do that? Maybe we don't need to do that. Maybe we need to plug in something else. So let's see what else we have. Let's just plug in p over q. What does that give us? And the answer is like, we don't really, at this point, we don't know what we're supposed to be plugging in here. It seems very complicated for this p and q. I don't see a quick way out here. And when you get to this point in functional equations, and trust me, when you do more difficult and even medium functional equations, it's okay to get that point. Then, you know, you just go like, okay, let me try to get some value. Let me try to get a half. How would I get a half? So let me forget about everything I have here, and let me just focus on getting a half and everything I can get with a half. So what happens when we're looking for a half? Let's plug in y is a half. Okay, so now we have here, well, we have this once we plug in a half. And the first thing, okay, like when I did do the same thing, if I plug in x equals 2, I'll get f of 5 over 2 plus, this is going to be 2 times 2 divided by 2, which is 1. F of 1 is 2, plus 2 is going to equal f of 2, which is 3, f of a half, plus 1. Okay, so I have this. Now I'm looking for these two values, 5 over 2.5. What if I look at, say, can I set x plus y to be equal to 5 over 2? And maybe set, like, can I get 5 over 2 somewhere else is now my question, and a half at another place, right? That is sort of like how I'm trying to like get out of this mess. And or something actually even that has a relationship between these two. And I invite you to pause for a few minutes and figure if you can put something in, and here's the answer. If I plug in x is 5 over 2 now, and y is 1, what do I get? I'll get f of 5 over 2 plus 1 is 7 over 2 is plus f of 5 over 2 is equal to f of 5 over 2 times f of 1, which is equal to 2 plus 1. In other words, these cancel out, and I have f of 7 over 2 is 5 over 2 plus 1. And now's a good time to actually see, like, wait, what did I just do? What just happened? And the answer is, I plugged in a 1. And what happens when I plug in y is equal to 1 is I have f of x plus 1 plus f of x is equal to 2 f of x plus 1. And the 2's and the f of x cancels out, and we have f of x plus 1 is f of x plus 1 for every rational x. We just looked at it on the integers, but it's actually true for rational numbers as well. And now with this in mind, right, what is this? This was like 5 over 2. 5 over 2 here, we have f of 5 over 2 is equal to 1 plus f of 3 over 2, which is equal to 2 plus f of 1 over 2. So this thing right here, 5 over 2 that we had, is in fact equal to f of 1 over 2 plus 2. And now, when this is 2 plus 1 is 3, we get this to the other side, we get 3 f of 1 over 2 is equal to, actually we get 2 f of 1 over 2 is equal to 3. In other words, f of 1 over 2 is equal to 3 over 2, 1 plus 1 over 2. So it seems like this thing could also hold for the rationals. Now, can we combine this in any way to get to a solution? I invite you here to pause for the next 10 to 20 minutes and try to push the problem further, maybe even finish it. And here's the next step. So now we go back to the original thing we had by plugging in y is equal to p over x, and x is equal to q, y is equal to p over q, x is equal to q, we get f of q plus p over q plus f of p is equal to f of q, f of p over q plus 1, right? And now we know this thing right here, because f of x plus 1 is f of x plus 1, and via induction, f of x plus q is f of x plus q outside, like we can prove this inductively. We now have this thing right here is equal to f of p over q plus q. And then we have f of p is p plus 1. Let's cancel the 1. We have q plus p is equal to q plus 1, f of p over q. Now the 1 p over q cancels out with this thing right here, and we get f of p over q is f of p over q times q is p plus q, and then f of p over q is p plus q over q, which is 1 plus p over q, which means that for the rationals we also have f of x is x plus 1 needs to hold true. And now here we've done the same thing we've done before. We have plugged in a bunch of values, not all the possible values, mind you, and we've got that this forced the function to give us a mapping from x to x plus 1 for every x that's a rational number. And now we need to check that for everything that we didn't plug in. This relationship, this equation will also hold true. And what happens is when we plug in f of x, when we check, this is called the checking part of the equation, when we check f of x is x plus 1, we'll get that the left-hand side is equal to x plus y plus 1, that's what this is, plus xy plus 1. And the right-hand side is going to equal x plus 1 times y plus 1 plus 1, which is going to equal xy plus x plus y plus 1, which is xy plus x plus y plus 2. 1, 2, x and y, xy, x and y. And with that, we have shown that this indeed does satisfy the functional equation. And given we force the function, like we've said, we've had a sequence of steps of reasoning that led us to this is what f needs to be. And so we finished the function. Now, this is the introduction to functional equations. There's a lot of things to put in here, but the first sort of principle is you want to have when you have a functional equation, a thing that holds true for everything globally, you plug in specific stuff and see what that forces this function to be. And this finishes up the problem, and as always, thanks for problem solving.